Hi, my name is Jasmine Bryan, and I'm from Madison County High School. My project is utilizing Eukaryotic Saccharomyces cerevisiae as an electricigen in both pure and co-culture in the anode of a microbial fuel cell. As society continues to use non-renewable fossil fuels, we must make changes toward viable green alternative energy resources. Microbial fuel cells have been given a renewed attention because of their ability to generate electrical energy from microorganisms. With this, I ended up developing a small-scale general proof of concept for a grander scale MFC design in the future, utilizing the understudied yeast as an electricigen and the emerging idea of co-culturing in the anode of an MFC for higher voltage. I then developed my hypothesis, which is if a co-culture of Saccharomyces cerevisiae and Escherichia coli is a viable candidate for electricigens in the anode of a microbial fuel cell, then the average voltage produced will be at or higher than the average voltage produced in a microbial fuel cell powered by pure culture of Escherichia coli or a pure culture of Saccharomyces cerevisiae. So with this, I utilized a dual chamber structure, which consists of a cathode, anode, and salt membrane. I also utilized two different organisms, that would be yeast and E. coli, and I did them as pure cultures, and then I combined them together as a co-culture. To ensure the E. coli was growing, I used positive control plates and a spectrophotometer to know the approximate cell counts before I added it to the anode. So for this experiment, I utilized three different groups. So I had a pure culture of E. coli, a pure culture of Saccharomyces cerevisiae, and then a co-culture of Saccharomyces cerevisiae and Escherichia coli together. And for each group, I ended up having three different microbial fuel cell trials. So from the moment when I submerged the electrodes into the anode and cathode, I connected I put the lids on, and then I ended up connecting the alligator clips to the copper wire, which was clamped to the voltage sensor. And from there, the data logger would then record a data point every second over a minimum of 24 hours. So by the end of this experiment, I ended up having over 900,000 data points because it recorded every second. Given all that data, I transferred over to my computer and I began interpreting and analyzing that data and producing my data analysis for this experiment. So here you can see a couple of pictures for my experiment. The middle one here shows a good setup. So you have the microbial fuel cell, the cathode, anode, and you can see the salt membrane. And then from there, it's sitting on a tray to prevent any leaking. If you look in the top right corner, you can see an example of why the tray was needed because there was a severe leaking in that picture. But for the most part, if we refer back to the other one, you can see where you then have the air pump going into the cathode, and you also have the alligator clamps connected to the cathode and anode, the black connected to the anode, and the red connected to the cathode. So the results. So for the first experiment group, we have the pure culture of E. coli, and trial 3 ended up having the maximum voltage of 0.29, and it also had the highest mean voltage of 0.22. For the second experimental group, this is a pure culture of yeast. It ended up having trial 2 ended up having maximum voltage of 0.31, and it ended up having a mean voltage of 0.16. The third group consisted of the co-culture, which is comprised of yeast and E. coli, and it ended up with trial 2 having the maximum voltage of 0.37 and the mean voltage of 0.28. So these next slides are going to be the results showing basically the overall data. So for the graphs here, this is the 24-hour overall results from the entirety of when it started to when I ended up calling the trial. So, and then you have the tables here, which is only which show the peak production. So from the time it first started to the time when it either hit zero, whenever you can see on the graphs whenever it hit zero, or it just started to plateau. Also, you can see in the first trial that there are less data points than the rest of them. The reason this is because we recorded this one in minutes. The data logger settings were set up weird, but in the future, we ended up utilizing a different data logger so that we could make sure that the rest of them were recorded in seconds. Here is the next one. This one's going to be a pure culture of cerevisiae. You can see as well that same thing. This is the 24-hour overall results and the graphs. And then again, you have the peak production for each of these as well from the start to the finish. Some of these ended up having different results, as a couple of them did leak in this one. So some of the numbers are different, and the production and of electricity was a bit different for these graphs compared to E. coli. So for this one, this is the 24-hour overall results of CoCulture, which is yeast and E. coli. And then you also have the peak production as well. And same thing here, these graphs give the whole thing, give the whole amount of data for the amount of time it was recording. And peak production is just from the start to the finish of that main peak of where it then hits zero once it ends. If you pay attention to trial 3 graph, you can see this one, it's a bit higher than the rest, but this one, if you refer back to slide 4, this is the one that actually had the most severe leaking, considering there was next to no liquids left in the MFC. And so I ended up calling this one early before the 24 hours because it was just giving off random results, data points. So I went ahead and called this one. So moving on, I now have my data analysis, to which I did 2 sample pair t-tests. This slide is showing the mean voltage produced during peak production. So for the first 2 sample pair t-tests up top, this is comparing pure culture yeast to CoCulture yeast and E. coli. And when I compare the t-value to the critical values of two-tailed 5%, this trial rejects the null hypothesis, and my alternative hypothesis has statistical merit. But when you do look at the second one, which is comparing pure culture E. coli to CoCulture yeast and E. coli, when I compared the t-values to the critical values of two-tailed 5%, the trial failed to reject the null hypothesis. So this is the next 2 sample t-test that I did. These both are comparing maximum voltage produced. So out of both of these, when I was comparing the t-value to the critical values of two-tailed 5%, the trial fails to reject the null hypothesis. And that was for both of these when comparing E. coli, pure culture E. coli to CoCulture E. coli and yeast, and when comparing pure culture yeast to CoCulture yeast and E. coli. So just to sum everything up, the maximum and highest voltage attained across all trials was in CoCulture, and the highest voltage was 0.31. Then out of the 4 2-sample t-tests that I ran, only one ended up being able to reject the null hypothesis, and that was when I was comparing the mean voltage produced in MFC of pure culture yeast to MFC and CoCulture yeast and E. coli trials during peak production. Because of this, my alternative hypothesis that has a co-culture of Saccharomyces cerevisiae and Escherichia coli is a viable candidate for electricigens in the anode of microbial fuel cell because the mean voltage produced across all trials is higher than the mean voltage produced in pure culture yeast, and it has statistical merit. With this, yeast can be used in pure culture, but it does show a more promising and being implemented into a co-culture in the future. As to what I would do in the future with my project, I would definitely experiment with some different materials. I did have to work with what I had at the time of this experiment. There are a lot more higher, more expensive materials. You're talking such as carbon materials, platinum, gold, and I don't exactly have access to that. Another thing that I would do is the design of it, the structure. I would definitely try to get that as strong as possible. Like I said, I did experience a lot of leaking with some of my trials, so I would definitely want to get that structure as good as possible before continuing to try and do another experiment to make sure that no leaking happens in the future. I would also, even with this, if I'm going to continue off of using the exact same ones, yeast and E. coli, I would definitely run more trials in the future. Like I said, had a lot of leaking. Some of them worked. Some of them didn't experience leaking. Some of them did, but definitely more trials are needed as some of the data is a little bit crazy as there was leaking. So more trials are definitely leaking, and that's just a part of the whole process. And more trials are going to be needed just to determine how reliable, viable, and durable MFCs can be so they can be further implemented in the future. With this, I would love to scale up my project just to ultimately see if there is significant data for large-scale applications and to see how they could potentially be used in the future as reliable alternative energy resources. And that's the end of my project. Thank you.